Hello everyone, welcome to the part 2 of the bellow design. In this part, we're going to remake our bellow problem following the same shape, but we have two models this time in one analysis. They have the same central distance, both of them are axisymmetric problem. The only difference from the previous analysis is now we use a shell element with natural thickness instead of a wine element, and the thickness is 1.5 millimeter. And for the bottom model, we make three shell elements. All of them has 0.5 in thickness, but uh, in the joint of the three elements, we actually use a cohesive contact for them. So we're going to compare these two cases and also compare to our previous result. And the way we draw it is first we create a central line for both model. These central lines are exactly the same as our previous simulation. So with the inner rotation diameter 50 millimeter and the outer diameter of 100 millimeter. And from this central line, we make the boundary for our shell element. And let's see the final element GUI settings.
Hi everyone, welcome to part 2 of the bellow design. In this part, we're going to use not a wire but the axisymmetric shell to actually simulate the bellow. And also we will compare the one layer versus three layers. So to create a shell, first we create a part. Let's do it one like let's call it one layer. So axisymmetric, and we need a shell. Again, similar to previous one, we create a point here, reference point, which is, let's do it 50, 0. And then use the linear pattern. And one direction, we don't need it. Two direction, we need 7 of it. And then create another point, 110. Sorry, let's create a point of 130. And then linear patterning this one. One direction, just one. Two direction, we can do 4 of them. Now you can see the shape. Connect everything just by simply clicking the points. And then create a Phillips. The Phillips is, again, we do 3 here. 3 millimeter. So this 2, this 2, this 2H, this 2H, and all of them you need to create a Phillips. So this is going to be your baseline, which is exactly the same geometry as your previous simulation. So now we need to offset the curve by a distance. So what we want is we actually create the 1.5 millimeter thickness. So that means to the left and to the right should be 0.75 millimeter. So select the curve you're going to offset, select this Philip corner down, and then offset by 0.75. It's pretty tiny, but you can see it's offset here. And it looks okay, so let's click OK. And then again, we need to do another edge. Now we can select by chain, which directly give you the entire curve. And then we click again 0.75. But notice that we want it to on the left, not on the right. So we use the flip. Now it's on the left. So everything look good. Click OK. Now we have 3 lines, but we only need 2 lines. What we create as the reference is actually not what we want. So we need to delete that. To delete that, we can use this one and then select all the thing that you want to delete. Make sure you didn't select the wrong thing. Sorry, this is a little bit hard to select. Okay, everything, remember to hold shift to select all of them and then click down. You will delete the thing. And finally, we need to close the curve. So connect this two and then connect this two. Once you're done, you should obtain something similar to this. And the mid-plane for this shape should be whatever you did for the previous analysis. And this is our first model, which is using only one layer of that. Then we create the second part. Before we actually create this, create a second part, the second part should be combined of 3 different parts. So basically it's like a split this part into 3 different parts. And later we are going to constrain this 3 and see what's the difference between these things. And okay, let's create a part. Let's call it middle model 3 mid. Again, axisymmetric deformable shell. So similar to exactly the same as previously. We do 0, 0. 50, 0. And then 100, 30. And then we do the linear pattern for this one. Direction 2, 7. Direction 1, 1. And linear pattern for, linear pattern for this one. Direction 2, direction 1, 1. Direction 2, 4. And then connect all of them. So this is going to be our our mid plane, and this time since we split the 1.5 millimeter thickness into 3 parts, so each part will take 0.5 millimeter, which means 0.25 to the left and 0.25 to the right. Let's do it. Oh, sorry, I forgot to create the Phillips. Again, 3 millimeter, and then just create a Phillips. Okay, once it's done, let's make the offset. Selecting this curve down and 0.25. So click enter. You can see it's moved to the left a little bit. Okay, and select this curve again. And make sure that you are selecting the reference frame, not the new created frame. So do it 0.5. It go to the left. We want it to be on the right. Okay. Now click OK here. Then finally, we need to delete what we have. So it's a little bit hard job. It's a hard job. So delete all of that. Make sure you didn't select the wrong thing. And finally, close the curve. Till you get a relatively thin one. And then we create the other part, which is one on the left of that, the other on the right of that. Let's call a side model 3 sides. And again, we do exactly the same thing. Like 50 0 and then 130 and linear pattern 1 7 and then linear pattern again 1 4. Oh, sorry, 4. Now connect all of them to give you the reference frame. And then create a Phillips 3. Down. Oh, sorry, I forgot. So now you have your reference frame. We create the offset. This time we want one on the left and one on the right, both with 0.5 millimeter of thickness, but one is definitely smaller, one is larger. So let's do this one. First, we do 0.25. So on the right, it should be 0.25 to 0.75. So 0.25, you see something on the right. And then click OK. Select this one again. Notice I don't select the wrong thing. Again, now we need 0.75. So these two are going to give you the new plate on the right. So we also need to create something from the left. So 0.25, flip, and OK. And select this one, 0.75. OK. And finally, delete what is useless. So this one. Okay, so when it is done, close your curve. Now you have the side one. So 3 parts, including the middle one, you should have a 3-layer one. In total, the thickness should be the same as the 1-layer one. We'll see later. So after finish the part, we assign the material property, which is quite similar. This should be your polyethylene and mechanical elastic and Young's modulus 100 megapascal, Poisson's ratio 0.35, and then we create a section. So for section, polyethylene section, so it should be a solid this time because we are shell element, which is plane string. So solid, homogeneous, and we want plane stress actually. So our thickness should be very small compared to our dimension. So the thickness is 1.5 millimeter. Let's do 0.01 in the third dimension. And finally, let's assign the section. We don't need to create sets. But first assign section on this one. From section, and then also don't forget your other part. In total, you have 3 parts here. Assign section, and already assigned. The model that already assigned turns out to be green, and this one is gray, so we need to assign that. So check again all your model, make sure that all of them is green. Now go to assembly. When assembling that, I would suggest make assembly of this two first. So I like to take independent here. So okay, you can see that the 3 are independent, but geometrically is kind of close to each other. So later we are going to add constraint to it. Otherwise, it's just 3 independent parts. So after we have that, we need to move it down a little bit. So select this one, translation the instant. Select all the 3 instant. Initial is just 0, 0, 0, and we want to move to minus y with 150. Now it's moved to something below the axis. The reason we do that is now we can create 1 layer incident, independence, okay. Now in the assembly incident, you can see that those 3 are kind of overlap with each other. So we translate this. We first need to hide this 2. So we only have this one, and then we do translation of this instant only and move it up with 150. So it go back to its original location. Now we can show this too. See, they're separated now. For the top one is your homogenized 1 layer model. For bottom one is your 3-layer model. So we are going to do analysis on these 2 models at the same time and compare them. Sorry, did I show this? Okay. And Now, after assembly, we can go to step to assign the step. Let me see. Oh, I think I forgot to confirm the translation. That's why it stay in the same place. So sorry about that, but let's do it again. So make sure you know like sometime how to do it. First, hide two of them, and then select the constraint. Select the instant you're going to translate and move up 150 of that, and then remember to click OK. Otherwise, you will like me. I didn't actually move it. So show now. It should be separated. And now go to step. You should still see those two different models. So now we can create the model, which is static analysis. Static. So 0.01, exactly the same as what we had before. Hit OK. Once we have the step, I would suggest to one thing is we need to later define the constraint, so we can make the surface first. To make the surface for this one, we can hide the mid one first. Now you can see the edge, and then at tools and surface, create, let's call it uh, side surf. Continue. So the side surf, we can change by angle and put a random number. Let's do 10 here. And select this edge and this edge. Double check it should be the inner of the side part, inner surface of the side part, to make sure it's the contact surface with the inner part. So done. And then hide the side, show the mid model and hide the side model. Now we can select the surface, calling mid surf. So select this one and this one. These two are the one that will constrain with your side model, and then show everything. And this is the surface for mid. This is the surface for side. They are coincident with each other. Later, we are going to assign a contact with this two. For the top one, we don't need necessarily to do anything. And then we can directly go to the mesh first. Similar to what we had before, we select the mesh control. You can use construct or free, but use the medical access. So then in your element type of this two, in your element type, you should have axisymmetric stress, but remember that we need to delete this reduced integration. So your element should be CAX4, which is a 4-node bilinear axisymmetric codahedra. So then we can assign the node. Assign the global node is enough for this too. So again, we do it 0.5. And then we can directly mesh it. Sorry, I didn't select that. Okay, once you're meshed, you can see clearly the node. This is actually 3 different instants, while this is just 1 instant. Once you get it, let's move to interaction 1. First, we need to create reference point for later to record the load and assign the displacement. So we make a reference point by directly selecting the point we want. Let's do model 1 first. So for model 1, we select this point. And then we create another one. For model 2, we select this point. So you have reference point 1 and reference point 2. Now we can make the constraint. First is constraint of the reference point, coupling the reference point, let's say model 1 RP. So coupling the reference point with the entire bottom surface. Select kinematic and everything, just leave it there. And then we do another coupling for bottom model. Select this one, coupling, let's say, what did I say before? Model 1 RP. So we create another model 2 RP coupling and select the reference point, done, and surface, select this one. Since you have 3 instants, you need to select 3 times. So everything keep the same. Done. And then we need to assign the interaction. To assign the property. To assign the property, we create a property first, call it like a cohesive contact. So we need a mechanical cohesive behavior, and then we can just leave everything default and create a property. And then we assign the property. Let's say it's during the step analysis. So it's a surface to surface contact. Let's call it cohesive contact. So we already have the set, which is mid surface. Well, your master surface is where you have the load. I would suggest the mid surface as a master, and slave surface is the side. And by doing that, you will have your interaction editing one. We choose small sliding and surface to surface, cohesive, and everything we can just leave it exactly the same. We don't need to change that much. You should see those contact at the corresponding surface. And then finally, we can make the load now. As we have before, we need to assign a compression force here. So inner pressure of a pressure, and then we select the surface, this one, and also this one. Sorry, I forgot to hold the shift. Check again, like they should all be your inner surface, and hit done. And then magnitude, we choose 5e minus 3 as exactly the same as what we have before. Make sure that your force is applied on this inner surface. And then we make the fixed constraint. So fixed constraint should be applied at this boundary. Make sure you didn't select the wrong thing. And also this 3 boundary, hold shift to select. So this top and that top use the fixed. Then we create a pre-described displacement. Displacement input. Displacement. So now we need to apply displacement on RP1 and also RP2. Hold shift. And U2, 25.4. Everything is exactly the same as previously, what we have. Double check your displacement pointing upward, which means compression, and everything looks good. Now mesh, okay. Oh, another thing I forgot is the history output. We can delete the original history output. What we need to create is, let's say, RP model 1, which is 1 layer. For this one, we need displacement. Sorry, I forgot to select set. I forgot to create the set for reference point. And yeah, in the 2 sets create, let's call it RP1, which is a geometry of RP1 only. And the other set is RP2, which geometry set of RP2. Now we can input our history output. Let's say model 1 layer, and select set RP1. And what we need is, we actually don't need stress. What we only need is the displacement. Actually, we only need U2 and also force, reaction force here. And that's your output. And then we create another one, model 2, 3 layer. So again, we only, set RP2. Again, we only need the U2 and also the reaction force. Okay. For your field output, you don't need to actually change anything. And then in your job, create a job analysis and memory, parallelization, we do 10 of that. So click OK, and everything looks good. So submit. Check your monitor. While the analysis is generating data, you can see those files are popping up, like data file, message file, status file should go more and more. 47 elements are distorted. That means the mesh is not very good. There's some weird triangle element. But since our element is a lot, that doesn't actually change too much. So it doesn't matter that much, but finer mesh always can help. Now the solution went to a total time of 1. That means the solution is done 17 steps. And we can see the result now. It's a little bit too dark here because our mesh is very fine. So we can add the option common. We can select free edge. So even with free edge, you can see that this has a boundary. This is 3 layer, definitely 3 layer, but this is only 1 layer. And if you really want to see, don't want any edge, you can output the no edge. Now it's more clear, like how this two model looks like. And you can see at the final stage, remember previously our conclusion is the stress concentration is applied, will be the maximum stress will be on the lower and bottom and top of the fillet. Now we are more clear that it should be located at the inner side of the fillet. That's the main difference between the shell element and the wine element. Wine element, you don't actually have a difference between inner surface and outer surface, but shell element, you can have it. Well, for 1 layer and 3 layer comparison, because our cohesive is applied, so it doesn't really change too much. If you really want to say what is different, you can see the inner surface, the stress is not as large as what is shown here for 1 layer. That means the cohesive layer, cohesive attachment cannot fully transmit the stress. And finally, let's see our plot. Towards data, create data, and then history output. And what we want is, let's see, we want RP1F. Let's name it as model 2 force. I don't know why it gets stuck, but let's see later. Let's create again history output, and then let's simply call it model 2F, which is model 2 force. I think I saved. Oh, sorry, this is filtered. That's why you couldn't see it. As long as you plot it, it's good. And then the other one is model 1 force. And then if you compare them, you can use the XY data manager. We don't need this one, delete that. We can create a set of XY data, which is history output. We need not this one. It should create it here called temp1, and also create this one. It should create it here, temp2. Let's do this two together. Now you can see the force different. That means for your model 4, which is a 3-layer one, your force to apply to the model is smaller than the 1-layer one. The stiffness has a little bit difference. And you can also output the data. To output the data, first create the XY data first, which is your, let's do create. So history output, for example, I want model 1. Let's do model 1 and model 1 force and model 1 displacement. If you plot it, it's just some random plot. It doesn't really make any sense. But then you can, in the report XY, you can actually output this too. So in the setup, we change that to call it data .txt, change it to txt is very important. And then just leave everything the same, and then apply. And you, in your folder, you should be able to see the data.txt here. You can use your Excel to open that. The new Excel import data, I actually don't know how to use it, because if you directly import that, it will give you just one column, which you cannot do further analysis. But if you, in the Excel, here we search for get data from text and select this one, you can pop up the text import visa, which is the old version for importing data. That one can help you split the different column, and then just finished. Save it here, and you will have all the data. So one of that should be the stress, which force, which is this one. We remember the force is 73. This should be the time, and this will be your displacement. So to plot your displacement and force relation, we can move it here, and then directly in your Excel use I like to use scatter with this curve. Now you can see how your force changes with displacement. And of course, you can output two of them and see what's the difference. And that's it. That's everything about our bellow design. And hope that you can learn something from this tutorial. Thanks for listening.